All right. So in the last couple modules, we've talked about elastic properties. And so now that we've kind of covered some of the basic elastic properties, I want us to go over an example in this module. All right, so let's get to the question. And again, as always, if there isn't an exam this week, then this will go on the quiz. If not, I still recommend that you work through this and compare it to the work that we show in a second. Okay, so the question here is to calculate the length and diameter when we have a tensile stress of 100 megapascals applied to a steel bar shown below. And so I give you the steel bar here, the length and diameter of that, and you have information about steel in this table 7.1, that you may need for those calculations. So see if you can determine the length and diameter when a tensile stress of 100 megapascals is applied. See what you get, and then come back and we will work this together and see if you get the same thing. All right, so let's take a look at this question related to the elastic properties. I resketched roughly the bar that we're talking about. It's made out of steel, and I copied down the relevant information from table 7.1. And then it's under 100 megapascals of tensile, so we're talking force in those directions of 100 megapascals. We want to know the diameter and length at that stress, and we know the dimensions initially or before that force is applied. So 5 centimeters from over here for the diameter and the length of 1 meter. All right, so let's look and see how to do this. So if we're looking for diameter and length, these are related to stress and strain, right? That's what we normalized by in each case. Length, the initial and the final length, right? That was a factor of strain. And stress was normalized by area, right? And the diameter is part of that area calculation. And so that's what we're going to do in this case, is we're going to look at both of these. So let's think about how to do this. We've got stress. Engineering tensile stress is the force divided by the instantaneous, tensile stress engineering is the force over the original area, right? So this value. It doesn't exactly give us this. However, if we can calculate strain, right? Strain is equal to the change in length over the initial length. And so we can get our instantaneous length because that's what we have here, right? So we can get this, and that's going to be what we have right here, right? So if we can get strain, we can calculate that. However, we don't have strain directly, right? But if this is linear elastic, then we know our proportionality constant between stress and strain is the elastic modulus, right? And we're given this in the table. So our strain is going to be equal to the stress divided by the elastic modulus, right? And so if we plug in those values, 100 megapascals for this stress, right, up here, and the elastic modulus, which we have as 207, but this is in gigapascals, so we're going to basically need to add 1,000 more, right? So that was in terms of megapascals because we're converting from giga. And so that value, if we calculate, is 4.83 times 10 to the minus 4. And again, these units cancel out, so it's unitless, as strain should be. Okay, and then we also know that strain is equal to that, right? So if we want to rearrange this to solve for the instantaneous length, then we can take the strain multiplied by the original plus the original. So just rearranging this expression. And so that would be the 4.83 times 10 to the minus 4 times the original length of 1 meter plus the 1 meter. And so if we do that, the instantaneous length is 1.00048 millimeters. Or sorry, meters. Right? It's a meter long, and so you can see how small of a change that it's made, right? So these elastic properties, it's elastic, it recovers, but only when the strains are very low, right? So you can see that this is hardly any change. So you wouldn't even be able to observe this type of difference. And the difference here, the elongation that we have is 483 micrometers, right? So that's basically half a millimeter. So you can't see this, right? You can't see this very easily. So that's just something to think about. So we've answered this first part. We got the length, right? However, again, we also want diameter. And we can't get diameter directly because of the way we define tensile stress as the force over the original area, right? So we need a way to find the instantaneous area and therefore diameter, right? And so if we kind of go through our repertoire of equations and terms that we've just looked at, the thing left is we've used this, but if we think about the Poisson's ratio, right? Poisson's ratio was looking at the ratio between the axial strain, which we just calculated, right? This was the length, and then the lateral contraction, right? And so that's related to this diameter. And so we can use Poisson's ratio since we have the strain in the axial, and we can find the lateral. So that's what we're going to do next. All right, so let's look at that. All right, so Poisson's ratio is minus the strain in the lateral, and we call that x, over the axial, and that we called z. So we know z, that's what we just calculated. We want to find x, and so x equals the Poisson, the strain in the x equals negative strain in the z times the Poisson's ratio. And so that value, which we had from up here, 4.83 times 10 to the minus 4, and then our Poisson's ratio from the previous table of 0.3. Sorry about that. And if we plug that in, our lateral strain is going to be equal to minus 1.45 times 10 to the minus 4. And again, the negative here means that we have a axial extension and a lateral contraction, right? So the thing's getting longer, but it's also getting thinner or less diameter. And so we can write the lateral as change in diameter over the initial diameter. And so if we do that, that would mean the instantaneous diameter minus the initial or original over the original. And if we solve for what we care about, which is this, di, and rearrange this expression, we're going to get that it's the lateral strain times the original plus the original. So plugging that in, we're going to get that number from up here, lateral strain, and then the original diameter. This was 5 centimeters, the diameter, and then add 5 centimeters. And when we do that, we see that the diameter is 4.996375. So I'm purposely adding a bunch of sig figs and decimals here so that you can see the small changes. And so again, it's basically rounding up to 5 centimeters, so you can barely see it. And the change in diameter is a negative 725 micrometers, so less than a millimeter. And again, it's contracting. And so that's what we have for the diameter, right? So if we have something like this that we can assume is elastic and everything is reversible, then we can apply Hooke's law, which we saw in the previous part. Where is it? Here, Hooke's law, to get strain from stress using the elastic modulus of the material. And then we can use Poisson's ratio to go from axial, which is part length, to lateral contraction, which is related to the diameter, which is what the question was asking.